This is the first lesson of Part 2 inside Unit 5 for college algebra. And in this unit, we're going to be discussing rational functions. Typically, at this point in the class, our goal would be to identify the horizontal and vertical asymptotes and then use an educated guess to sketch the behavior of the tails. But I'm going to modify that for this video. Instead, what we're going to do is we're going to go out to Desmos.com. We're going to use Desmos to graph these functions. And our new goals today are going to be, number one, how do we identify the asymptotes by analyzing the rational functions? And then number two, how to identify the behavior of the tails. Tails are sometimes called branches. I've even heard them called arms and legs before, and you'll see what I mean in just a second. So how do we identify the behavior? Essentially, how can we sketch a graph of these functions by doing some simple analysis on the function itself? Now, if you're not aware, a rational function is simply a quotient of two polynomials. So p of x is the phrase that we would use for a polynomial. I don't want to use the letter p a second time, so I'll use the letter q. If p and q are both polynomials and I were to divide both of them, then that's what creates a rational function, and we use the letter r to denote rational functions pretty frequently. So by looking at this equation and performing some analysis to it as necessary, we should be able to identify where the horizontal and vertical asymptotes are. Now, if you recall, an asymptote is a vertical line or a horizontal line that kind of denotes a position where a function may approach, but it tends to not cross or touch. So if we had two asymptotes here, we might see the graph that is kind of captured by those asymptotes, where the graph will, again, approach this vertical line or approach this horizontal line, but never touch it. Now, we almost never cross or touch a vertical asymptote, although it is possible for us to touch or cross a horizontal asymptote. Sometimes we see graphs that behave kind of like this, where they may come up and cross the horizontal asymptote, but then they level off towards it again. Or sometimes we even see these oscillating patterns where the graph tends to bounce above and below, but eventually level off at that asymptote. And we would still call that asymptotic behavior. So let's see if we can identify those. Now, again, I'm going to use, or identify the rules to establish those. I'm going to use a graphing calculator such as Desmos in order to do this fairly quickly. And I've already got this function put in right now. R of x equals 2 divided by x minus 3. So here's that graph, and it certainly looks like this graph has a horizontal asymptote at the x-axis, and we can mimic that, or we can reproduce that with the equation y equals 0. Anytime that we have y equals a constant, that's going to produce a horizontal line. And I'm just going to change the settings on this to make it a dotted line. Now we know that that's an asymptote, not really part of the function itself, but an imaginary line that the graph approaches. Now, as far as the vertical line goes, well, this may take some scaling. And if you're on a touchscreen device, it might be pretty easy to adjust the zoom. I'm actually going to exaggerate the x-axis a little bit, make it much wider, and then zoom out just a little bit, and maybe scrunch the vertical axis some. This allows me to more clearly see that vertical line, and it definitely appears that this graph is approaching an x value of 3, but it's not touching or crossing it above or below. It may look like that it touches, but if we were to zoom in real closely here, you'll notice that that red line doesn't actually touch an x value of 3. So I'm going to recreate that graph here with x equals 3. To create a vertical line, we're using x equals. And if I press the settings gear, I can adjust the style to be dotted again, and I'll go ahead and make it the same color as before. And there we go. So here again, we've got horizontal and vertical asymptotes, so I'll make a note of that. We have a horizontal asymptote, and I'll use HA for that abbreviation pretty frequently. We have horizontal asymptote at y equals 0, and we have a vertical asymptote at x equals 3. And so while we're completing these examples in this video, I want you to think about what does it take in order to create these asymptotes. How can we identify those asymptotes by looking at the equation or performing some analysis on the equation represented by the function? So I'm going to adjust the scale here just a little bit. Each of these hash marks indicates that there are 2 units per grid line. So now here's this vertical asymptote at x equals 3. Here we have the horizontal asymptote at y equals 0, and we can sketch the curve surrounding that. Now, this branch or this leg was actually in the bottom left-hand corner relative to the asymptotes, and then this branch here was in the top right-hand corner. So after we establish our rules, how we learn to identify our asymptotes, it's going to be just as important to understand how to identify the behavior of these tails or these branches. How do we know that the tails are going to be in this position, and why weren't they in, say, this position or this one? So we'll try another example and see if we can establish some rules. I'm just going to turn these graphs off by tapping the icon here on the left-hand side, and I'll be able to create a new one. This time, again, I'm going to use r of x to represent a rational function. It's not necessary that you use r of x. You could use f of x just as easily, but I do want to use function notation in case we end up creating data points to go along with this. I'm going to press the divide symbol first to create an empty fraction, and then I'll fill it in with 3x plus 5 over x plus 2. So now we have 3x plus 5, over x plus 2. Again, a similar graph here. We've got the 2 branches or 2 arms or legs to this graph. Definitely appears to be leveling off at some value as well as some vertical value too. It's approaching but doesn't quite touch. So this time to me it looks like the horizontal asymptote is at y equals 3. So let's check that. If I graph y equals 3, yep, sure enough, that looks like a line that the graph approaches but doesn't quite touch. And then as far as our vertical asymptote goes, well, I don't know, that scaling's a little bit different there. Let's see if we can fix this. I might say 2 on this one. X equals -2. Let's see. X equals -2. There's that vertical line, and yep, I think that's a pretty good guess too. So I'm going to make that match the format as before. And again, we've got a vertical asymptote and a horizontal asymptote. This time, our vertical asymptote was located at x equals -2, and we had our horizontal asymptote, this time not at y equals 0, but y equals 3. So in a similar fashion as before, I might adjust the scale. Each of these hash marks indicates that the grid lines represent 2 steps instead of 1. And we have this horizontal asymptote at y equals 3, vertical asymptote at x equals -2. And if I double check the graph, this time the graph appears to be in the top left-hand corner and the bottom right-hand corner relative to those asymptotes. Not relative to the origin, but relative to the asymptotes, the intersection of those asymptotes. Top left and bottom right. So I wonder why that's the case this time. Why does the graph sit up here and down here as opposed to the bottom left and the top right? Have you been able to formulate a guess as to what the rules are to establish our asymptotes yet? That's going to be our first objective. Let's take a look at this guy. Now, I don't know about you, but I noticed something that was kind of interesting, at least with the denominator in the first 2 examples. We had a vertical asymptote at x equals 3, and when x equals 3, something interesting occurred in the denominator here. And up here we had a vertical asymptote at x equals -2. And when x equals -2, we have that same interesting thing occur in the denominator. Now, it's going to be hard to identify when that event occurs. Hopefully you recognize what I'm talking about. It'll be hard for us to identify that in this particular form, but if I rewrite the numerator's polynomial and the denominator's polynomial in factored form, we might just recognize some consistency here. So let's do that. In the numerator, this trinomial factors to x plus 1 times x minus 5, and in the denominator we have x plus 1 times x plus 3. These two are common factors, so we can cancel them, and essentially this graph is going to simplify to x minus 5 over x plus 3. So I'm just going to think about that for a second, and I'm going to make an educated guess myself, and I'm going to check that with the graph. If nothing else, I think I've got a pretty good idea of where the vertical asymptote is going to be. So I still want to graph the original function. I'm not graphing this guy, because that's a simplified form that's technically not exactly the same as the original. We'll get into that discussion at another time. But I want to graph this original function, and I'm going to use the analysis that we've done so far to predict the behavior of this original function. So I'd like for you to make your guess right now, too. Think about what the behavior of this function might be, and resume playback in a moment to check your work. Now, if you were thinking like I was thinking, it certainly looked like an x value of -3 would have made this denominator equal to 0, and I think that might have been the location, or I was thinking that that was the location of our vertical asymptote. So when I jumped over to Desmos, certainly that's exactly what happened. So we've got a vertical asymptote at x equals -3, and let's see about our horizontal asymptote. That kind of looks like y equals 0 again to me. But we do have to be careful with that assumption, because take a look at what happens over here. The graph does tend to cross that line, but it never flattens back out, never levels off to that. So y equals 0 won't be correct. But watch what happens here. Let me just try to adjust this zoom. We'll exaggerate that vertical axis. Can you tell what that horizontal asymptote might be now? It's kind of hard to see with that vertical asymptote in the way. How about instead of y equals 0, we get y equals 1. Now we've got that horizontal asymptote where the graph is tending towards, and it approaches but never quite touches. And I'm going to make a note of that on our notes here. We had a horizontal asymptote at y equals 1. So horizontal asymptote at y equals 1, vertical asymptote was at x equals -3. And the graph was kind of interesting because it existed in the top left-hand. This branch existed in the top left-hand corner of the asymptotes and in the bottom right-hand corner. Now, one thing that I want to point out here, and this will hopefully tie into what I said or what I mentioned a moment ago, this equation is technically not the same as this equation, even though we used equal signs in between it. And here's the reason why. Watch what happens if I plug in a number -1 for x. -1 minus 5 divided by -1 plus 3. Well, that looks like -6 divided by 2, which would be a -3. And that seems reasonable. When x is equal to -1, we get a y result of -3. Now, my scaling, of course, was not great for this sketch, but that, again, seems reasonable. But watch what happens if I try plugging in a -1 to this equation, the original one. What would happen if I plug in -1 for r? And this is part of the reason why I use that r of x notation back here, because with Desmos, I can simply type r evaluated at -1. I ended up getting an undefined result. It doesn't equal -3 at all, or -3 at all. I ended up with a undefined result. So what gives? Why is that the case? We're essentially saying that when x is equal to -1, we end up with a little hole in the graph. This is where those holes come from, if you've ever seen this notation before. Why is there a hole there? Well, I mean, think about it. What happens if you plugged in a -1, especially in the denominator here? -1 squared is a +1. 4 times -1 is -4. If I had 1 minus 4 plus 3, that equals 0. And now we've got a 0 result in the denominator, and we can't have that. Because regardless of what the numerator is, any value divided by 0 is undefined. And you may have also noticed that the number -1 would have made this factor equal to 0, and we would have seen a similar result. This is what we call a removable discontinuity. Removable discontinuity. And this is our way of saying, well, the graph is not continuous right here. It becomes discontinuous at this location. There's a tiny little break in the graph at that one position. This value here, which ended up creating our vertical asymptote, is what we would call a non-removable discontinuity. And hopefully you can see the similarities. In both cases, we call these a discontinuity because the graph breaks. It separates at these x values. The removable discontinuity, well, we call that removable because it was factored out and disappeared. This removable discontinuity created a hole in the graph, whereas our non-removable discontinuity, what couldn't be factored away, ended up creating an asymptote. So here again, the features and behaviors of our graphs are going to be determined without the use of a graphing calculator eventually. And by now, I hope that you're starting to establish some rules to figure out these behaviors. Now, the only thing we haven't really clearly identified yet are the rules for the horizontal asymptotes, but with these last three examples, hopefully you're starting to form an educated guess here. Let's see if we can test that guess with this example. I think before I do anything, though, I'm going to factor first, and once I'm finished factoring, I'll identify any discontinuities. This will help me find any holes or asymptotes, vertical asymptotes anyway. And once I've identified the discontinuities, the holes and the asymptotes, then I would probably try to sketch a graph. And if I can't sketch a graph by considering the holes and the asymptotes, what might be helpful is if I use some test points. We haven't done that yet, but if there's a need to do so, I think using test points to identify the behavior of these branches might be helpful. So here we go. Let's start with the factoring. Now these are non-standard trinomials, so factoring can be a little bit more challenging. It's not going to be as easy as finding two numbers that multiply to equal A and two numbers that multiply to equal C. We've got to think about the FOILed result. What format, what type of factors would FOIL back together to make this original term? Now we are lucky in the sense that there are only two factors of 3 and only two factors of 1. Well, one factor of 1, if you will. So this is the combination that must be used. Now, in order to FOIL back together to make a middle term that's equal to -2, is going to require a -3, but a +1. And I put the negative sign here because I know that this -1 will multiply by 3x in the FOILing process, thus producing a -3x. This +1 and this x is going to multiply together to make a +1x, and -3x plus 1x gives us the -2x that we were after. In the denominator, similarly, we see 2x and x. That's the only way to multiply to equal 2x squared. We also have to use a 2 and a 1 in order to multiply to equal 2 and 1, although these two values could be switched. We could put the 2 here and the 1 here. So let's make an educated guess and check our results. Is it possible for the outside factors and the inside factors to add together to make the middle term? Well, on the outside here I have 4x, and on the inside I have 1x. Can 4x and 1x combine to make 3x? Well, certainly. If I had a positive 4x and a minus 1x, that would be correct. So if I put a minus sign here and a plus sign here, then we have an appropriately factored denominator. Now this is kind of interesting because as far as our discontinuities go, none of our factors are removable. So based on what we've established so far, we should see two vertical asymptotes, one at -2 and one at +1/2. Those are the two x values that will make the denominator equal to 0. So I'm not going to adjust the scale this time, but I will mark a vertical asymptote at -2. And I will mark the horizontal asymptote at +1/2. Oops, sorry, not a horizontal asymptote. I don't know what I'm thinking. I have another vertical asymptote, I should say, at +1/2. Again, vertical asymptotes are the result of the denominator equaling 0. I think that's what we've established so far. So x equals 1/2 and x equals -2. But now how about the horizontal asymptote? Well, what I've noticed so far is that in this case we had a horizontal asymptote of 3, and that was the result of these leading coefficients dividing by one another. Here we had a horizontal asymptote of 1, and that's again these leading coefficients dividing by one another. In this case we ended up having a horizontal asymptote at 0, but I noticed that there was no x value up here, or if there was an x value we would have imagined that to be x to the 0th power. So I have my suspicions about that, but again in each of these other cases the leading coefficients created the horizontal asymptote, and these leading coefficients were part of terms that had the same degree. And that's exactly what we have down here. We've got a pair of leading coefficients and the leading terms have the same degree. So I'm going to go out on a limb and I'm going to make the guess that there's a horizontal asymptote at y equals 3/2. Now I don't really know what's happening with the two vertical asymptotes, why we have that, but at least preliminarily I think I've got an idea of where this, where the behavior of these branches might be captured. So I'm going to jump out to Desmos now and I'm going to sketch this original function. And so I've already entered that into Desmos, and we see this result here. So this is kind of an interesting occurrence in the center of the graph. And if I put on this vertical asymptote, x equals -2, and this vertical asymptote at x equals 1/2, that seems to support our initial guess, or my initial guess. And then when I insert the horizontal asymptote at y equals 3/2, that seems to support it as well. So as far as our sketch goes, we are still bounded or captured by these asymptotes. This one over here kind of produced a traditional branch, and this one down here produced the traditional branch that we're used to seeing. Because of those two vertical asymptotes, we saw this interesting occurrence in the center here, and here again is an example of a line crossing the horizontal asymptote, but that's okay. And so our initial guesses, I think, were supported here, but there's still some oddities that are occurring, and I don't quite understand what's happening in the center here, and I don't quite know what to do next. Oh, you probably just heard the bell ring. I am recording this just before class starts in the morning, so I do have some students coming in. I'm going to stop the video now. I'm going to ask that you use Desmos to graph these last two examples and then recreate those graphs on this page here. Do your best to identify the horizontal and vertical asymptotes on your own first, and then check your work. And then lastly, read through this series of data points, or this series of instructions at the bottom. This will help solidify how we find our asymptotes of rational functions. And while the language may appear a bit foreign at first, I bet you'll be able to interpret it now that we've established some rules on our own. If you have any questions, please let me know. You can reach out to me by email or as a message through Schoology, or bring it up in class next time we see one another. Thanks for watching.